All right, welcome back to the section 4.1 video. In this video, we're going to take a look at another example of forming a general solution to a homogeneous differential equation using the idea of linear independence, forming a fundamental set of solutions, which gives us a general solution. So we have a different type of differential equation that we've been seeing so far in this lesson, that we have a third order differential equation because we have a derivative, a third derivative. So we have y triple prime minus 6y double prime plus y 11y minus 6y equals 0. So we have three solutions because we have a third order differential equation. We have y1 equals e to the x, y2 equals e to the 2x, and y3 equals e to the 3x. So we want to see if these are linearly independent. We want to see if these three functions are linearly independent so that it could form a fundamental set of solutions so that we can create our general solution. So the way we would verify that solutions are linearly independent so that we could get our general solution is compute the Wronskian. So let's start our solution off, and what we're going to do is compute the Wronskian. Okay, so we have three solutions now. So e to the x, e to the 2x, e to the 3x. We've mainly been dealing with just two solutions. Now we have three. So this is going to give us a different type of determinant, a 3 by 3. So when we have a 3 by 3, we're going to need to take a second derivative. So we write our solutions here in the first row, and we're going to create two more rows with their first and second derivatives. So e to the x, chain rule 2e to the 2x, chain rule e to the 3x, and then our third row. This becomes 4, this becomes 9, using the chain rule. So let's make this a little smaller. Okay, so with a 3 by 3 determinant, it's a little different. We're still creating a determinant. We're still cross multiplying, but when we do a 3 by 3 determinant, what we do is create a subset of more determinants. So we're going to reduce this to a 2 by 2 determinant. And the way we do that is really our solution term. So let's look at e to the x right here. E to the x is in this first column right here. And it's in this first row right here. So my determinant is going to be e to the x times the remaining 2 by 2 terms left in this determinant. So it would be e to the x times the determinant 2e to the 2x, 3e to the 3x, 4e to the 2x, and 9e to the 3x. So I'm obtaining a new determinant. Let me move this down really quickly. Give us some room. Okay, and so that's my first new determinant. And so what we need to do now when we get our second determinant is we need to subtract. We always subtract the second determinant. So let me erase some of these highlights. And so our next determinant would be corresponding to our second term, e to the 2x, and e to the 2x is in the second column, we still cancel out the first row, and so our remaining determinant will be these terms right here. Sort of cut off by the middle, but this would be our new determinant. So our second term was e to the 2x, and our new determinant would be e to the x, e to the x, 3e to the 3x, and 9e to the 3x. Okay, so we have three solutions. We're going to have one more determinant. And so let's erase these highlights and circles. And so with this third determinant, we're going to add, subtracting is only for the second determinant. And so we are focusing on e to the 3x. So third column, first row, my determinant remaining would be these terms off to the left. So this would be, my third term was e to the 3x times e to the x, 2e to the 2x, e to the x, and 4e to the 2x. Okay, so we're still computing the Wronskian. We just now have three determinants to take care of, but we just treat them as we normally would. Let me erase some of these highlights. Okay. And we would just treat it as we normally would by cross multiplying. We just have a lot more terms to take care of. So what we would end up with is e to the x times 18. E, we're adding exponents, so e to the 5x minus 12 e to the 5x minus, careful with the negative, e to the 2x times 9e to the 4x minus 3e to the 4x plus e to the 3x times 4e to the 3x minus 2e to the 3x. Okay, so things simplify down quite easily since all of our exponents are of the same terms. So becomes e to the x times 6e to the 5x minus e to the 2x times 6e to the 4x plus e to the 3x times 2e to the 3x. Okay, great. So now we can multiply in our terms. So e to the x times 6e to the 5x. Now we're adding our exponents, which becomes 6e to the 6x minus 6e to the 6x as well, plus 2e to the 6x. Okay, so the 6e to the 6x terms cancel out because they're subtracting. And what I'm left with is 2e to the 6x. And remember, we're computing the Wronskian. We're trying to see if these three solutions are linearly independent. And so, oops, excuse me. And so the way we determine that is, does the Wronskian equal 0? No, it never equals 0 because an exponential function never equals 0. So we know for a fact this would never be 0. So y1, y2, and y3 are linearly independent. Okay? So therefore, the general solution, it would look like, y equals c1 y1 plus c2 y2 plus c3 y3 for this third order. So it's y equals c1 e to the x plus c2 e to the 2x plus C3 e to the 3x. And that's our general solution. So, a little bit of a different flavor since we had three solutions. We needed a 3 by 3 determinant, but hopefully this answers your question on how we would do that. And the fourth order, we would do the same exact process and fit six, but I think three is about as high as we want to go in this course. So yeah, just kind of backtrack. We verify that the solutions are a fundamental set of solutions by showing they are linearly independent. So we could say are linearly independent and form a fundamental set of solutions. And since they form a fundamental set of solutions, therefore they are a general solution to this homogeneous differential equation. So, okay, that's it for the homogeneous general solution introduction. Thank you for watching, and I'll see you in the next video. Okay, take care.